In this video, we are going to start by discussing force. Force is our first new vocabulary word for this particular unit. And force is an interaction between two objects that could potentially lead to a change in motion. We'll discuss a little bit later what I mean by potentially, but I do want to emphasize here that when we say change in motion, we're referring to a change in velocity or in acceleration. The units for force are going to be newtons. So this is going to be the first of our series of units named after various scientists from the past. And a newton is the same thing as a kilogram meter per second squared. So rather than having to repeatedly write kilogram meter per second squared, we're going to abbreviate that by just writing a capital N. This is why it is so important to convert everything into SI units, because a newton is a kilogram meter per second squared, not a kilogram kilometer per second squared. So if you leave your distance, for example, in kilometers, it's not going to properly cancel out with a newton, and you're going to find your answer is going to be off by a few factors of 10. Now, there are two categories of force. The first category is a contact force, and a contact force requires contact between what is exerting the force and what is experiencing the force. So you actually have to have physical contact. So this is not Harry Potter where you can use your magic wand in order to move an object. You actually have to touch the object to move it. So I'm going to be asking you a lot, what is touching the object? Because that is how you're going to identify what type of contact forces are being exerted on the object in question. The other category of forces is field forces. These do not require contact between what is exerting the force and what is experiencing the force. So you're in the field of the object exerting the force, and you still experience that force even though you're not touching that particular object. So the one we're going to discuss in this particular course is the force due to gravity. So we've already hinted that a little bit earlier, and we understand the fact that the Earth pulls on an object as it is falling. We talked about that in free fall and in projectile motion. So we know even though we're not touching the Earth still pulls down on us, and that's why you go up and you come back down when you throw an object up in the air. There are other types of field forces that would be discussed in other physics courses. So next semester, if you're taking Physics 102, you may see something like magnetic force or electric force that are also field forces. So let's talk about how we calculate the force due to gravity. We're actually already familiar with the components of it, we just need to put them together. So remember, the force due to gravity is a force. Weight over here is the scalar term for the force due to gravity. So force due to gravity is a vector, weight is a scalar term. So you should think force and weight together once again, just like we talked about in topic 1. And the force due to gravity is going to equal the mass in kilograms times what we were calling the acceleration due to gravity, but we'll call the gravitational field strength. So the gravitational field is what actually exerts the force due to the mass, like the Earth, exerting that force. So that gravitational field strength is going to be in meters per second squared. Sometimes it's also easier to think of it in terms of newtons per kilogram, so how much force you get per kilogram of mass. It is very, very, very important that you learn the difference between these three terms and recognize the difference between the units. Because one of the most common errors I see when we start working with forces is that you use the mass or the gravitational field strength instead of the force. So it's very important to know what units go with each term and to know that we're adding together forces. So you need to add the force due to gravity to other forces, not add the mass or the gravitational field strength. Now we are going to discuss Newton's first law of motion. Newton's first law of motion states that an object moves with a velocity that is constant in magnitude and direction unless a non-zero net force acts on it. Alright, so let's dissect this a little bit. So what it is saying is that the change in velocity will be 0, because when the velocity is constant, Vf minus Vi is going to be 0 because they're the exact same number. And this means that the acceleration is 0, which is going to mean that the force net acting on the object is 0. Now, net means that you're adding together more than one force. But when you add together that force, some of them are going in the positive direction, some of them are going to be in the negative direction, so that the total is 0. So you only get a change in velocity and an acceleration when your net force equals some value other than 0. So we're now going to explore this using a simulation. In the simulation, we have a tug of war over a cart of candy. So what I have represented up here is the sum of the forces. So right now nobody is touching the ropes, so there is no forces acting on the cart. And you also see down here there is a speedometer. So the first thing I'm going to do is I'm going to put a person here, and you'll see that there is a force to the left, and because it's the only force acting on the object, that the sum of the forces is just equal to that force to the left. So when I hit go, the cart moves to the left. Because there is a non-zero net force, there's going to be a change of velocity, so you're seeing that in the speedometer. And because that force is acting in the left, it's going to move to the left. So let's reset this. Now, if I take and put up a blue person, you'll notice that there's a force to the left. And if I put up a red person, there's a force to the right, but they're equal and opposite, so the sum of the forces is 0. And so when I hit go, the cart does not move because the sum of the forces is 0. Alright, now let's take the red person off. So we're going to move to the left. But now if I put the red person back up, notice that the speed stops changing. So let's return and let's try this again. I'm going to start with the red person down here. I'm going to hit go, so notice that the speed increases. And then when I put the other red person up there, the speed stops moving. And the reason for that is, remember that net force leads to an acceleration. And that acceleration causes a change in velocity. So when there is a net force that's causing an acceleration, that's causing a change in velocity. But when the net force is 0, there's no acceleration, so there's no change in velocity. So there are two conditions where you can have a net force equaling 0 and thus an acceleration equaling 0. One, when you're at rest, and you saw that before, where the two forces were equal but opposite and the object never moved. Another condition is when you have constant velocity. So there was some initial velocity, but then when we put an opposing force, the velocity stopped changing even though the object was still in motion. The velocity was just a constant value.